So yesterday we established that if theta is in radian, limits as theta tends to 0 of sine theta divided by theta is always 1. We established this yesterday. So the first thing I want us to do is to be able to apply it into a few questions before anything else. In the worksheet question 7, last two questions, you have to use a similar principle, one of them to prove the perimeter of a circle, okay? And the other, what was the other one about? Something about a sector. So it's a similar idea, okay? I need you to prove that and try to make sure you prove it yourself, please. Okay, think, not maybe consult someone to help you out, okay? Because this is like, okay, if you have something like that in exam, what will happen, all right? So let's listen to this example. If you want me to explain further, I think Karen and I were talking about this even yesterday after class. So just to understand, yeah, I think Ethan also was wondering why something cannot be 0. I hope everybody is clear now. Let's listen to this example. Hopefully I'm sharing the right screen. Yeah, can you see? Okay. And I've shared the audio. Nice. Okay, let's see. I put it in maximum volume first. All right.
In this section,
do you hear that? Okay.
We consider trigonometric limits. A particularly important trigonometric limit is the limit as theta tends to 0 of sine theta over theta. For theta in radians, this limit is equal to 1. This is known as the fundamental trigonometric limit. The limit might be surprising because when theta equals 0, both numerator and denominator are 0, and therefore the expression is undefined. What it means is that as theta approaches 0 from either side, sine theta approaches 0 at the same rate. We can use the fundamental trigonometric limit to evaluate other limits involving trigonometric functions. In this case, we consider the limit as theta tends to 0 of sine 3 theta over theta. To use the fundamental trigonometric limit, we need to divide the sine of the angle by the same angle. The angle here is 3 theta, and we only have theta in the denominator. So, we multiply by 3 over 3. We take the constant 3 out the front, and we recognize that in the limit as theta tends to 0, 3 theta tends to 0 also. Now look at the limit. We have the limit as an angle tends to 0 of the sine of the angle divided by the angle. This is the fundamental trigonometric limit, which is 1. So, the limit as theta tends to 0 of the original expression is 3.
Does that make sense? And just, sorry about that. Just to remind us, yesterday, we looked at this on decimals. Can everybody see decimals? Okay. We looked at it on decimals. This is sine x divided by x. You could see clearly that as x tends to 0, this is in radian, it's not in degree, that's why you have 1, 2, 3. You can see clearly as x tends to 0 from either side, this curve moves close to 1. That's what the fundamental trig limit is talking about. Okay, but from the question, let's see, sine 3x divided by x. Can you see that? As x tends to 0, can you see it's moving close to 3? That's the question you have just solved. Either from both sides. You know, when we talk about limit, we talk about the two-sided limit being existing, and they must be the same. Am I making sense? So from the left, okay, from below, you have moving close to 3. Also from above, you have also moving close to 3. Does that make sense? So the only problem is we should be able to manipulate the expressions, and also you have to change the limit. So you see, you have to change what it tends to also to be the same. I was telling, was it Karen and Ethan yesterday, that you will see that the same variable here is here and it's also here. Until you have that, you cannot say it is 1. That is why in our explanation also in class, we had to make sure everything becomes the same before we were able to establish the last one. If you look at the first thing to be proved yesterday, the first proof, let me see. No, not yesterday. I think that was the class before yesterday that we established. No, it was yesterday. It was the last thing we proved yesterday, right? If you look at your note, the first thing was we proved that the limit as n tends to infinity, right? Okay, that doesn't give me 0. That doesn't give me 0. Okay, forget about that. Then we're able to use that to prove the main results. Okay, so this is not exactly it doesn't exactly look like this. So my point is, if theta is moving close to 0, definitely multiple of theta is also moving close to 0. Just see it as theta is equal to 0 implies 3 theta is equal to 0, something like that. Okay, so this is just something you just put in a bracket to justify why you change the variable that the variable and the value the limit is moving close to. So I want us to practice this. First, I want you to do A. Okay, try A. I'm sending everything. I'll send from here. Let me send the example first. Then I'll pick what you need to do. So start with A. After A, attempt B. So attempt A and show me, then attempt B. B will require some sort of manipulation. So it's okay if you don't know how to manipulate that. Just indicate immediately. I show you something you need to do. You need some other properties of limits. By properties of limits, you are able to break the function into rational form. You are able to break it into product form. You will need a combination of all this. So please speak up if you do not understand what to do. Okay, receive something. Yeah, that makes sense, Mr. Chang. Go to the next one. Just let me know if you need clue. Nice. Larissa, well done. Yeah, Calista, that makes sense. Nakita, you are sending to the group. You didn't get enough sleep, right? I can see that. Nakita, you didn't get enough sleep.
I need to drink coffee.
You didn't drink coffee. All right.
Mr. Daniel, can you give
Yes,
a hint
sir.
for B?
What?
You give a hint for B.
Oh, yes. Give me the question again, so I don't open two different windows.
Limit of theta over sine theta.
Mm-hmm. As theta tends to zero.
Theta approaches 0.
So remember, this is what we need. We need it to be theta as numerator, right? So you have your limit as theta tends to 0. Then you can have sine theta divided by theta, theta divided by theta. So basically, I multiplied by 1 over theta divided by 1 over theta. Can you see that? So that my numerator will be 1 and my denominator will be that. Then you can apply this property. Limit of f divided by limit of g is equal to limit of f over g. You understand? Some properties of limits. Some properties of limits. If you have limit of rational function, provided g of a is not equal to 0. The limit is limit of f divided by limit of g separately. You can break it down. I mentioned it yesterday. So you break it down. This is limit of 1 divided by what you need here. Okay?
Okay.
Then you can apply constant, limit of a constant. That's how you manipulate it. Krista, are you lost? Krista C. You're lost.
Yeah, I'm not so understand.
You don't understand. Okay. Why don't we do this? Let's do it together. If anyone also has problem with 2, so just let's do this together. Then you can use the idea for the. So the question is limit of theta over sine theta as theta tends to 0. If anybody finished 2, please go to 3. I want us to practice enough there today. So clearly, this doesn't make sense as far as that rule is concerned. So you try to rearrange it by multiplying by the same thing top and bottom. You see that? Okay. But instead of wasting your time to say multiply, you can actually just say this means limit theta tends to 0, 1 sine theta over theta. Can you see that? So I move this downward. So which is what is happening here. Because this is b theta over theta 1, this is something like that, okay? If you don't want to go explaining this, you can just write directly. With this now, because this is a rational function, yes? This looks like a fraction. So this will be limits as theta tends to 0 of 1, while this is the limits as theta tends to 0 of what you need. Okay? So this is the fundamental trigonometric limit at the bottom, isn't it? So at the bottom, you have 1. At the top, limit of a constant is a constant. So the answer is 1.
Okay.
So go to C, guys, or you can check your B with what I've just done. Karen.
Yes.
In your B, you wrote limit theta tends to 0, 1 over sine theta over theta. Then you change it back to limit theta over sine theta is equal to 1. We don't have
Yes.
we don't have any results for that. That is that you just came back to your question. And the reason for manipulating is because there's no rule for the question. So that would be a wrong thing to do. Please follow what I did if you are not clear of how to manipulate. Nakita, I've received it. Move to C. And show me how you did your B separately if you have done this differently. Aha, yes, Ethan, your presentation makes sense now for B. Can Krista make sure you don't turn when you're taking a picture, because now I have to turn my head. Okay, that makes sense. I've seen that. Miss V. Yeah, that makes sense, Vienna. Calista, well done. 1 bit. So let's try C. Let's try C. Let's try D. Someone's got a coffee now. Cheers with your coffee. Cheers. You can ask questions regarding C, D, E if you want. I haven't done it as well, but we can always think about what to do. Yes, yes, yes. C. Can anybody give me an idea how to do C?
Wait, I'm almost done.
Okay.
I was in the picture.
From Ethan and Lillian. Nice. Correct, Mr. Chang. Okay. Lillian, did it say 0 divided by 1 or 0 times 1? For your D.
Times, I wrote wrong.
Yeah. You didn't get enough sleep, that's why. So for that 0 times 1, you could actually just say sine 0 because that is a direct substitution, isn't it? Just in case someone is wondering, how did you get 0? So that you can do as substitution. So please show sine 0 times 1, which is equal to 0, something like that. So that would make sense. E, okay, I'm looking at your E, F, and G now. Okay, G has not been done. Let's look at E.
I skipped a lot of working.
Okay, you shouldn't skip next time, please. So I see how you can move things around. But of course, the answer is correct. I'll try. Thank you. Put me out to type. It's okay. No problem. It's good. Thanks. Okay. It's correct, but I will need full details next time, okay? Miss V, something came in from you. No, Vena, no. This is not. So you have tan is sine over cos, yeah? That second line, are you looking at what I'm saying from your book? The second line, limit sine over cos times theta, is correct. And try to write it as theta cos theta, so it doesn't look as if cos theta theta, that it doesn't look like the angle on cosine is theta theta. Okay. You know what I mean? So try to write it as theta cos theta, that's one. Secondly, you can break it into two parts. It's product. Product of what looks like your fundamental trig limit, which is sine theta over theta. And another product is 1 over cos theta. Okay. So if you see them as two different functions, f and g, then you can say limit of f times limit of g. So one of them can take direct substitution, which is the 1 over cos theta. That would just be 1 over cos 0. And 1 over cos 0 exists. Okay. Then sine theta over theta can take the property that has been established. Understand? And that's how you get the answer. Not giving each of them limits. There is no rule that says you give them separate limits, remember. Because if as you have given them separate limit of theta as theta tends to 0 is 0. That's exactly what we are trying to avoid. Having 0 as denominator. Understand? So redo that, please. Miss K, checking your work now. Oh. Uh-oh. Karen did it another way. Let's see. This seems correct, Karen. However, can I ask you to do another way?
How? I
Yeah.
don't know how to do it.
Yeah, I'm gonna tell you, don't worry. So come to the board with me. Because we are trying to use the fundamental trig limit, which is this one. Can you see the board?
Yes.
Because we're trying to use that, so I want every solution to be connected to that. So the question is limit tan over theta, right?
Yes.
So this is simply limit theta tends to 0 in theta cos theta. Do you agree?
Yes.
So this is simply limit right?
Yes.
So split it into two limit products, or product of two limits, where this is the result established. Remember, it's a single function here, and now you're breaking it into two functions. Okay?
Yes.
So I don't think you will actually get 0 with this. It's not 0, and you got 0 in your results. So what's the first one?
0.
What?
Not 0.
Sine theta over theta.
Oh, 1.
1.
Oh, okay.
And this is a direct substitution. 1 over cos 0. What is cos 0?
1.
1. So what's the answer?
1.
And plot the graph to see. Let's look at decimals. Let's look at my decimals. Yeah. Okay, just a minute. Okay. So tan x divided by x as x tends to 0. So x is equal to 0 is the green line, right?
Mm-hmm.
Right? So if you are coming from the left, if you're coming from here, you're going to follow this one, right? Then there will be a break. There's a break somewhere here. Then it appears again from the top, and it's going to be close to 1.
Yeah.
If you're coming from, this is left, sorry, this is right. If you're coming from the right also, then it comes here, it disappears, and it reappears at the top, and it goes to 1. So the limit is 1 as it moves close to 0. As x moves close to 0 from both directions, the limit of this function is this line, and that is 1. So not the 0 that you got.
Okay.
Okay? All right.
Yes. Can I ask what I did wrong in my
What you did was to establish, okay, wait. Yeah, you brought in cos squared. Where does cos squared come from? Okay, you know, it's sine over cos, right? And what you have at the bottom there is theta, not cos.
Oh, yeah, okay.
So your sine theta over cos theta divided by theta, when this comes down here, it should be this. But what you wrote is sine theta divided by cos squared theta. As if theta times theta is the square, something like that. So that's what you did wrong.
Okay. Thank you.
Nice. Yeah, this is correct, Ethan. Well done. Mr. C, checking now. Yeah. Krista, you did it differently from what I just did, and this is wonderful also. So you have 1. There's something here to notice, Krista. Krista C. Can you see your work? Now, if you look at this point, you see here, this is okay. This is brilliant. So you put this up and you have separate limits. I love that. However, before you change the limit, you cannot have different limits and move the variables around. Krista?
What's that mean?
Okay.
Different limit.
Okay. So you already have one single limit here with different layers, sort of, if I may call it different layers, right? By the time you break it into 2 different limits, this cannot be manipulated anymore. So this should come first with a single limit. Okay? Because with a single limit, this is one function. And within one single function, variables can move to wherever. But the moment you separate it into 2 different limits, one is numerator, one is denominator, they become individual, separate entities. You can't just move things around anymore. That's one observation. So you should change this to a single limit. Okay, change this to a single, so which means this step will come here first with a single limit, and the second step we now have with different limits. You get what I mean? That's one. Another thing is, if you have them as a separate limit, like the last step will look like this. Like, understand? Once you get here, you can't have one limit anymore. You just write 1 over the limit. So this limit is for the bottom one, not for the both of them. You get what I mean? This limit here. Because it is this numerator that gives 1. Yes? So it's actually 1 divided by limit of cos theta. So it's not limit
so I need
of
to
1
write
over
the
cos
limit.
theta. 1 is, you are done with the top already. Okay? So exactly, this is now correct. Look, this is correct. Because having cos 0 is actually doing the direct substitution, but the limit is only for the denominator, because numerator already gives you 1 by that fundamental trigonometric limit. Understand? So readjust your workings and send back to me. So let's look at more. Uh-oh, not you. I think that is correct. I'm checking your C now, Clarissa. Clarissa? Clary?
Yeah.
Okay. Yeah, this is like too much work. How do I say? It's not, you still get your answer, but it's not an efficient method. You don't need the sine over cos times, sine over cos divided by sine over cos step. You don't need that. From your sine over cos theta divided by theta, are you listening?
Yeah.
You can manipulate directly. Look at what I put on the board. Can you see what I put on the board?
Yeah.
Sine over cos like this, you can just split into 2 separately like that. You don't have to multiply by sine over cos divided by sine over cos. You get what I mean? Talk to me, please.
Okay, yeah.
So I adjust that, and you still get the same answer, though. Adjust it, please. Thanks. Lillian, she said no sure. Well, I hope you show details work this time. Then I can trace what is wrong. Sine over that, so you multiply by that, yes. Lillian, so somewhere you have n tends to infinity changing to 3n over y tends to 0. Yeah, you could do that, or you could just say, let 3 pi over n be x. Is that okay, Lillian? So you could do that. That would be better and less confusing. Oh, let 3 over pi divided by x to be n. I'm sorry, 3 over pi divided by n be x. Okay, so if you do that, then you can make n the subject. You can make n, if 3 over pi divided, let's see. Look, what you did also makes sense because with n tends to infinity, 3 over pi over n will tend to 0. So that's the way you change that limit makes sense. Then you multiply by 3 over pi divided by 3 over pi. Then n will cancel n, 3 over pi is left. 3 over pi comes out. Yes, this is correct actually, but just for simplicity, you could change it to x if you want, but this is also perfectly correct. That's correct. Calista. Yes, because it is sine square. Wonderful. Wonderful. So Calista, are you listening? You see the other part of that product. That's the limit of sine theta as theta tends to 0. Okay? Take one more step. Okay? Why the first one becomes sine? Instead of writing 1, why the first one becomes 1? The step 1 times 0 is what I'm referring to now. Instead of 1 times 0, we know why the first bracket is 1. It's a rule. Okay? But for the second one, just write sine 0 first. Before you write 1 times 0, which is equal to 0, not 1 anyway. 1 times 0 is 0. Last time I checked. Maybe you didn't get enough sleep. So you wrote 1. Okay. Miss V checking some work. D. So you split them into 2. Perfect. Nice, nice, nice. You already explained what I want in the big because as theta tends to 0, sine theta tends to 0. Or you could just say 1 times sine 0 because that is the direct substitution, Venom. Understand, Venom? If you do not have a rational function, you can substitute directly, remember? So that's sine 0. So it should be 1, it could be 1 times sine 0, which is equal to 1 times 0, which is equal to 1. So that makes sense. So the way you've explained is also acceptable. Mr. Cheng, checking your works. Wait. Ethan, I thought you said you're not supposed to be here now.
My eyes kind of work, so it's okay.
Okay. Maybe you updated the operating system of your eyes this morning. All right, so let's look at this one. 3 pi over pi. Okay. Makes sense. Then 3 pi went outside the limit, while this looks like what we want. As that happens, this tends to 0, you change the limit. This is wonderful. Brilliant, Ethan. Brilliant. Krista C. Nice. Krista, this is now a better presentation. It's well presented now. Clary, I'm checking the good. This is now better. This presentation is better now. Clarissa, for D, you had 1 times 0. Did you see that line, 1 times 0?
Yeah.
So you could just go a step further. Before writing 1 times 0, you write 1 times sine theta. The first part is a result, so you can write 1. We don't need to know why you got the limit of sine theta divided by theta to be 1. We already established that. It's a rule. It's like a formula. But the other one is something that we always do ourselves. So the limit of sine theta as theta tends to 0 is a direct substitution. So if you could show me sine 0, so I know what is responsible for each one. Do you
Okay.
understand? The first one is the fundamental trig limit. The second is just a direct substitution. So 1 times sine 0 before you write 1 times 0. You understand that? So that's all I need to say about that. Nakita, checking this. Nakita, you skipped too many things. Limit, sine, can you break it into 2? For that D, I need it breaking into 2.
Okay.
Sine theta over theta times limit of sine theta. The first one gives 1, the second one gives sine 0. Then you work from there, please. You skip too many things. Karen, I'm checking yours now. Yes, the first one makes sense. That's C. The second, I'm checking D now. Same thing I'm telling everyone, Karen. Limit of sine theta as theta tends to 0. If you could write the first part as sine 0 first. So we know what you are using for each part. It's just giving more explanation, even more than necessary. Do you understand, Karen?
Yes.
First part is a direct substitution. Show me how you substituted sine 0 into sine. So that's sine 0 times. The second one, you don't need to show me anything other than 1 because it's a fundamental rule.
Okay.
Yeah, right. So now in number E, I can see 1 times 4 times 1. I don't know where 4 times 1 comes from.
Okay.
I don't know where that comes from. So you need to think about number, was it A or B? Number A. So what you did in number A is needed for the second part of E. So, and that needs to be shown in your calculation.
Okay.
All right? Okay.
Yeah.
Okay, Ethan, I'm checking H. This is H. Check the question from the book. You don't have to open multiple windows.
Yeah, it's H.
Okay, okay, got it. So if you need that to be 7, you have to multiply by that. Nice. Yes, yes, yes. So in the bracket of the third step, you can put in bracket as x tends to 0, 7, x tends to 0. So we know why you have used that thing. Okay?
Okay.
Yeah, every other thing looks perfect. Well done. Lillian, checking. Yeah, H also makes sense, Lillian. Good job. I. Okay, let me see how you did the I. Okay. Okay. This works. What I was thinking, Lillian, is that from the beginning, couldn't you split x squared plus x divided by sine 2x into x squared over sine 2x, 1 over sine 2x? I'm not sure if that will work though, but this is correct. This is correct. This makes sense logically and everything. This is correct. You can think about what I said if you think that would work or not, or you can just leave it this way. So E, Miss V, I'm checking your question E now. Yeah. Good, nice. Good, Nakita, I've checked the D now, it's correct. E, E is also correct. Good job. E is, look, second to the last step in E. The first one is 1. The second one is 4 times 1. Write that 1 in the bracket so we know, okay? 4 times 1.
Okay. Okay.
Just to indicate that, yeah, this becomes 1. Yeah, so everything now becomes 4. So just write that in the bracket.
Okay.
Okay, so after this, we'll move. If anyone has finished, can you try question 2B? Okay, 2B, that would be the last one, please. 2B. Even if you have not finished the whole of question 1, you can always try them later. But I want everyone to look at question 2B now so we can move on. Clarissa checked. Well done. Krista, I'm checking your work now. Wait, is Krista K in this class? She doesn't seem to be here, right?
I think she's still sleeping.
Oh no, can somebody call her phone? Krista C, she called you last time. You need to do the call now. Oh no. Please call her
I called
phone.
her, but she didn't answer her.
Oh no, this is what happened to you last time too. Your phone was on silent. She called you, you didn't answer. Oh no, I just realized, oh my God. Let me also try to call her. So you guys are not just foodies, you're sleepyheads too. Good to know. Okay, so I'm checking your work, Crystal. So Crystal, what I told everyone in question D is that the second to the last line, where you wrote 1 times 0, preferably I would like 1 times sine 0. 1 is an established rule, but how does 0 come about? Oh, I did direct substitution because that is allowed for that function. Okay? So write sine 0 before you write 1 times 0. Just that. E is perfect. Also in F, where you wrote limit of cos h as h tends to 0 as 1, you could write cos 0 first. Okay? Just to explain further what you are doing. Every other thing looks okay. Lista, check in. So you have to. No, you don't multiply by 1 over 4, Callista. You multiply by 4 over 4. So the 4 at the top, because when you multiply by 1 over 4, you've changed the question. I'm talking about E. You sent me E. Now, how did you do your B? Go back to your question A. Can you go back to question A? Did you see times 2 that you did? And there's a 2 already there, 2 theta. So that's like multiplying by 2 over 2. Understand? So it is actually multiplying by 2 over 2, so that is more or less 1. So nothing has changed. And you need a 2 at the bottom to make it look like the fundamental trig limit. while the other 2 is just staying at the numerator. And that is the same thing you're supposed to do in number E. So you can multiply by 1/4. 1/4 is not 1. So that means you already changed the function, which doesn't make sense, okay? So change that. And also, I don't know how you get 4. So that 4 should come outside the limit. So because at any time, and also, you still have your theta tends to 0. Please go back to question A again. Your question A, oh, I should have corrected something. Go back to your question A. You wrote 2 times sine 2 theta divided by theta as theta tends to nothing actually. That should have been 2 theta tends to 0. And you already put the reason in front that as theta tends to 0, 2 theta tends to 0. But where's your 2 theta? You never used it. So you might go to the example again if you need. The example is actually on your screen too in that question, in the screenshot you sent me. So you could see it. You could see that you have missed something. Okay, so adjust that and send back to me, please. If you need help, please tell me. Clarissa, I'm looking at your question F now. Nice, you split that first, then you manipulate this. Yeah, that's correct. And you change, good. That's correct. Mr. Chang, this looks nice. Okay, I'm checking your 2B now. Uh-oh. Low battery. Oops. Yeah. Check on decimals first. Something is not clear to me here. Function is cos x over x. Step x tends to 0. Okay, tends to 0. So you should get 0. Let's see what you did again. So you have h sine square h over h squared and times h. So you still have one h on the bottom. Nakita,
Yes.
so I'm checking your work now.
Mm-hmm.
So you have sine square h. So you multiplied by h over h, correct?
Yeah.
Okay. Can you write on this step where you have your minus sine square h? Can you write times h over h by the side next time?
Okay. Okay.
So now I know why you have sine h over h all squared. Nice, clearer. Then you just put 0, 1 square. No. Can you break it into different limits? Not just 0, 1 square. Please, you skip too many things. You need
So
to
I
start doing
separate
that.
them.
Yes.
Right.
It's more explanatory. Do you see that I know explains everything? What's going on? Is it the coffee that's not working? So separate them. The limit of negative h, the limit of, in fact, the negative can be outside. So minus limit of h times limit of, sine, even that square, it needs to be explained. For example, if I have limits of sine h over h all squared, I don't want you to just write 1 square. I want you to write that this is actually limit of sine h over h all squared. That's why it is 1 square. Not just this one is 1 square.
Okay.
You understand?
Yeah.
And this is a rule that the limit raised to power any whatever is the same as the limit of the function raised to power something like that. Remember this rule. Understand?
Okay.
So state them, be more explanatory. Yes, your work is correct, but please show more.
Okay.
Lillian, I'm checking yours now. I like how you break it instead of going through. Okay, you have that. Okay. So you didn't do that. You just split it into minus sine h. Okay. Now, Lillian.
Hi.
Can Lillian hear me? Okay.
Hi.
Okay. I need to find where your video is. All right. So you have sine h squared. Is that divided or times? Because you already have it as 1 over cos h plus 1. That is just times, no longer divide. You agree? Do you agree with what I said?
Yeah, I
Okay,
wrote
so
wrong.
change that to time. Then also your minus sine h. That function has a negative, so it should be a bracket. Or you can put the minus behind the limit. Okay? Then that big bracket will not be necessary because this is time. So the bracket will become redundant. You don't need that. The answer is correct, just the way you have put it. So please adjust that. Okay?
Okay.
Callista, your correction has been noted for 1E and it makes sense. I didn't ask you to do 2A, Callista. I asked you to do 2B. Isn't that what I ask everyone to do? 2B, not 2A. Okay, so I think we have done enough of limits because of our time. I'm just going to explain the discontinuity so we can leave the class soon. It's already 12:30. I can't believe we spent 1 hour practicing limits, but that's good. Love that. Very good. Very good. Very good. Very good. Can I please ask everyone to suspend what they're doing? Feel free to practice more and send me stuff, ask questions. I'm still checking your video. You're still doing something. I need everybody's attention. Thank you. So Lillian and I are the foodies this morning. That's good to know. That's good to know. We are the foodies this morning. Anyone in the foodies club? Callista, is that food? No, it doesn't look like food. Okay. So continuity, that's the last part. Then I'll give you time to practice this on your own. It's going to 1 p.m., so we need to quickly do this. Now, existence of limits of existence of f of a and limit of a are useful in describing the continuity of a curve. Continuity means it's continuous like that. Understand? Okay, it continues like, oh, it's a smooth curve, sort of. Am I making sense? The path, if you are going, if a tiny object like the ant is traveling on the curve, is everybody please watching what I'm doing? I need to be sure that your eyes are on the board and you're not doing something else, please. Thank you. If you have, by any chance, where do I put this now? Just a sec. Now, if a curve is drawn, let's look at this one, for example. If something is traveling from here, like a tiny insect traveling, then the insect wouldn't be able to go through because of this, right? It's like, oh, the road has been damaged. Or you get here, oh, you need a ladder, okay, to jump to this one, right? Or you get here, oh my God, I need to like jump down and make sure I do not fall into this ditch or whatever it is. And, you know, something like that. So if a curve looks like what we are used to normally, like the sine curve, it's continuous like that. So this aspect is all about that continuity of the curve. Now, the fact that f of a is, we know f of a is the y value, remember. It means when x is equal to a, f is equal to, y is equal to something. Do you agree with me? Okay, so this f of a and the fact and limit are always used to describe continuity. Now, when do we say a function is continuous at a point? Listen, function is continuous at a point. Two main conditions, actually about three. F of a must exist, because if f of a does not exist, then there's no continuity at that point. Are you getting my point now? F of a must exist. The limits of that function at that point must also exist. And this f of a and the limit must be the same. So these are the three. Just a sec. So you have a curve. Okay, you have a curve. This is x is equal to a. We will say this function is continuous at this point, x is equal to a. If, let's trace it. Oh, it has a value when x is equal to a. It means f of a exists. Understand? That value, let's call it big A. Are you with me? Also, limits of f of x as x tends to a also exists. How do we know that a limit exists? If the limit from below of f and the limits from above, are you with me? Exist, and both of them are equal. So that's it. So this is condition 1, this is condition 2. And condition 2 must have satisfied these 3 conditions too, right? The third, oh, this limit that exists must also be this value. F of a must be that limit. So look at this in this way. F of a exists, you can see, at this point. At this point, we are not saying at every point. This continuity is about that point. Understand? At this point, oh, f of a exists. Okay? If you try to find a limit, if I come from this side, oh, this is the point of convergence. Right? It keeps coming like this. Okay? If I'm coming from this side, okay, from below, this is also the point of convergence. So the limit at this point exists. Are you with me? And the limit is actually this point. And this same point is your f of a. Then we can say f is continuous at a. At x is equal to a, actually. I should write at x is equal to a. F of x. F of x is continuous at x is equal to a. If the following holds. So 3 conditions. F of a exists. At first, we are not talking about what f of a is. Limit of f of x exists. As x approaches a also exists. And that means we have taken care of the limit from both sides. These 2 must give you the same result. Understand? Then you can say that function is continuous at that point. Now, if the function is not continuous at that point, you say the function is discontinuous at that point. You can either say f of x is discontinuous at maybe point x is equal to b. Another way, you can say f of x has discontinuity at x is equal to b. Or you can say f of x is not continuous. You are still saying the same thing. Not continuous means discontinuous at x is equal to b. Does that make sense? Understand everyone what I just said? So let's go back. You don't need to worry about all this too much. Okay, it's the same thing that we have talked about. Okay, but you will see soon. Now, if it is not continuous, we say it is discontinuous or has discontinuity. Yes. Now, if there's a discontinuity, please listen. Karen is looking down. I don't know what she's looking at. They're supposed to be looking at the screen. Everyone's supposed to be looking at the screen. Now, if it is discontinuous at that point, now this graph explains better everything I want to talk about. Graphically, we have seen that isolated point of discontinuity are indicated in this graph, yeah, by a O. This is what we call a O. I'll tell you what brings about the O very soon. A jump or a break. We see jump discontinuity. We see jump discontinuity, especially in piecewise function. Do you remember the piecewise function graph we drew yesterday? And there were jumps. Hello? I think I saved one from yesterday on GeoGebra. Let's see if I can open it. Open recent piecewise function. Okay, not this one. This is not. Okay, let's see this one. Oh. Aha. Watch my screen. Look at this. Can you see jumps? I sent this to you yesterday, I'm sure. Okay. So there's a jump from here to here. There's a jump from here to here. You always see jump discontinuity in piecewise functions. And this is the equation responsible for it. Otherwise means x greater than or equal to 0. Otherwise means every other interval that has not been mentioned. We use otherwise last. Okay? Is that understood? Like this one now. If I use otherwise, it means I've considered 0 also. And 0 is not considered here. Look at it. 0 is not considered. So if we zoom in, x is equal to 0 is not taken care of. Nothing is said about when x is equal to 0. X is equal to 0 is not taken care of. There's no answer for it. Okay, Desmos will have given that better. Anyways, so let's go back to that stuff because time is not on our side. So discontinuity discontinuity are indicated by 3 things here, and these are the 3 different discontinuity you can be seeing. Okay, you can see a O, then you know, oh, there's a discontinuity. You can see a jump, you can see break. Now these 3 things that could cause discontinuity now can be grouped into 2: removable or essential. Removable means, yeah, it's a discontinuity, but we can remove the discontinuity. I'll give you an example. Where's my pen? Okay, I'll give you an example. Look at this function. I want the whole class to tell me what to do. I want to find the limit as x tends to 2 of x minus 2 divided by x squared minus 4. By direct substitution, this is my f of x, right? Does f of 2 exist? No. So if this is f of x, my f of 2 does not exist. Do you agree? So which means it already failed the first rule. Okay? So it means it is discontinuous at that point. Are you getting that? But then we can still find the limit. Are you with me? We can still find the limit. How do we find the limit? We can remove that point that is causing, that factor that is causing the discontinuity by saying, oh, limit that. Then we have that. When this is removed, can you see? Then yes, we can now find the limits. When you plot the graph, at that point you put this. Are you with me? So this is what they mean by, these are the examples of the removable discontinuity. So you see, it should go like it's a smooth curve, right? But the problem is actually at that point there's a hole. Are you with me? For jump, I told you this is for piecewise. For break, Think of break discontinuity as your rational function, the vertical asymptote. Am I making sense? At that point, it will never give us that value. It will go, then it will appear again somewhere. It will never cross that line. Okay, so now listen to the last part of the explanation. If f has a hole at x equals a, then f of a exists. You have seen that from the example that I just gave you now. The hole is a removable discontinuity, which can be removed by defining a new function based on f, but which takes the value of f of x at x equals a. Isn't that what we have just done in that example? We have removed x minus 2 factor, thereby getting 1 over x plus 2. But 1 over x plus 2 is not the original f, isn't it? So we have actually defined a new function. A new function is that 1 over x plus 2. It's not the same as the original function f, but it's based on f. And it will take the value of the limit of f at x is equal to a. That's what we have just done. Does this make sense, everyone? Okay, everyone, make sense? Because I can't see everybody at once, so I have to move to Nakita's screen, Kalista and Vena. All right, so again, we have a hole at x equals a. How do you know you have a hole? If you substitute directly, it does not exist. But what causes that undefined can still be removed when you factorize. Then you know you have a hole at that for that function at that point. So we call that removable discontinuity because you can still find the limit. It's a discontinuity, we know, but it's a removable discontinuity because you can still find the limit by rewriting. When you factorize, when you simplify, you can now get a new function. Let's call that g. That g is based on f. And the limit that g gives you is the limit of f of x at that same point of discontinuity. Understand? So that's a removable discontinuity. The other two, the jump and the break, you can't do any magic to them. Okay? Those ones, we call them essential discontinuities. Discontinuities due to jump and breaks cannot be removed by simply redefining the value of the function there. They are called essential discontinuity. So again, only discontinuity that is due to a hole in the function can be removed. Every other discontinuity cannot be removed. They are called essential discontinuity. The other one is called removable discontinuity. So there are actually two major discontinuity you can experience: removable or essential. Removable discontinuity is caused by a hole, and it is removable because you can actually manipulate, write a new function by removing something that would have given you undefined. Essential discontinuity, you cannot do anything because they are due to jump and break in the function. Does this make sense, guys? Okay, so finally, before we go in 7 minutes, let's listen to this tutor. Then the rest is up to you. There are numerous questions here. Some of them are already in the paper that I gave you. So it does end as question 7 here. Please take your time. I intentionally didn't take all the questions from here, so you have enough questions to play with as practice on your own. I took them from different other sources also. So let's listen to this, and that will be the last thing for today. Please, if anybody still has questions, feel free to talk to me. I'll try as much as possible to reply. Can everybody see the self-tutor screen? Okay, and please give me a thumbs up if you can hear the audio and properly. We have 5 more minutes to go.
A function f is continuous at x equals a.
So it looks like there will be a recap of the stuff, okay? I want you to also listen to this part very well. If you need more explanation after, I will explain. When they say, okay, let me quickly say this. F is also continuous, so this definition is enough. So if I ask you, when is a function continuous at x equals a? This line is enough for you to tell me. If f of a and the limit of x at a exists, and these two are equal, then f is continuous at that point. Okay? Otherwise, it is not continuous, or you can say it is discontinuous. We can now talk about the kind of discontinuity later, but it is continuous is the first question. Now, another way they have explained it in your book is that if A is the left end point, it's like saying from below, okay, is the left end point on which the interval is defined, and f of A as well as the limit from above exists. Can you see that? So indirectly, you are taking care of both directions. A is the left end point for which the interval is defined. So it means from below, it exists already. Then f of A and limit from above exist and are equal. Or the other one, A is the right end point. Right is from here, isn't it? Okay, A is the right end point of an interval for which f is defined. Then f of A itself, as well as the limit from below. So in either of these two definitions, you are already taking care of both sides. Do you understand? But you don't need to worry about it. It looks too long and complicated, which is why I didn't mention it. And you are not an analysis student in university, so you don't need some of these extensive details. This is simple enough for you. That's why I used that graph to explain it. So this is enough for you. Understand? So let's listen now. Lillian will worry about the long definitions later.
A function f is continuous at x equals a if f of a and the limit of f as x tends to a both exist and are equal. Notice that there are also specific conditions for the endpoints of an interval. If we are considering the left endpoint, then we need the function to be defined at that point and its value equal to the limit as x approaches from the right. If we are considering the right endpoint, then we need the function to be defined at that point and its value equal to the limit as x approaches from the left. If f is not continuous at x equals a, we say that f is discontinuous or has a discontinuity at x equals a. Graphically, there are three different types of discontinuities we can identify: holes, jumps, and breaks. A hole is regarded as a removable discontinuity. We can remove it by redefining the function so that at that particular value of x, it takes the value which is the limit of the function as x approaches that value. Jumps and breaks are essential discontinuities, which cannot be removed. With this background, we consider the functions in the example. In part A, we have the reciprocal of a linear function. It can never be 0, so y equals 0 is a horizontal asymptote. It is undefined when x equals 5, so this is a vertical asymptote. The limit when x tends to 5 does not exist, so f is discontinuous at x equals 5. This discontinuity is a break, which is an essential discontinuity. In part B, we have a piecewise function. It is 1 for all x greater than or equal to 0, and -1 for all x less than 0. The function is defined for all x. However, the limit of f as x tends to 0 from the left is -1, but the limit of f as x tends to 0 from the right is 1. So, the limit of f as x tends to 0 does not exist, and f is discontinuous at x equals 0. This discontinuity is a jump, which is an essential discontinuity. In part C, we again have a piecewise function. The function equals x squared when x does not equal 2 and equals 6 when x equals 2. The limit as x tends to 2 from either side is 4. So the limit of f as x tends to 2 is 4. However, since f of 2 takes a different value, f is discontinuous at x equals 2. This discontinuity is a hole, which is a removable discontinuity. We can remove the discontinuity by defining a new function g based on f, but which defines f of 2 as 4. You should notice that g is simply x squared for all x.
Can you see that now? The last one especially, because instead of this 6, okay, why don't we redefine the function so that we can use this dot to block this hole? Which means for all x, your g is the f of x. That's the summary of this. Okay? That's the summary of this. So this is the last part of the limits as far as our textbook is concerned. This is the last part. So after this, we can now go into difference. So I'll send this to us all. Please practice and also, discuss some of these 4 and 5. Could it be removable, blah, blah, blah. So you need a sketch. Okay, make sure you sketch to be able to see. Okay, make sure you sketch to be able to see. Okay, then when this is continuous, please try this out also. I'm happy to give you example if you need me to. And some like 6 and 7 might be more complicated. You can try also if you want, but especially up to number 5, you should be able to. Then if you go to your revision exercise, I will send all this to you also. This is one of the homework that I gave you. It's similar to the one we proved in class. Do you understand what I mean? So I need you to make an attempt. Another one is this. It is also similar to what I gave you in class. This is number 4. This one also is similar to what I gave you in class. Actually, the second part. The first part is normal math. IGCSE, IB, Form 4, 5 stuff. So that's all about that. Then we can begin differentiation by first principle next time. Any questions, please? Okay, we go now. Sorry, 2 minutes extra. Bye. I'll upload the video soon. Then you can watch the review. Okay, thanks.